Today in lab, we'll be doing a simple colorimetric analysis of potassium permanganate. It's building on the concept we learned last week in the light law, the light properties of light lab, where we're going to use a UV-vis spectrometer to determine the concentration of an unknown. Because of the nature of this, we're going to take a calibration curve of known concentrations and then test the absorbance of an unknown of the same substance, an unknown concentration of the same substance. And from there, we can correctly identify what is its molarity. So we'll be splitting this lab into two, maybe three parts, where first part is make the dilutions, second part is make the calibration curve, and third part, test the unknown. See you in a minute.
Okay, so I'm going to be making my potassium permanganate solutions and making the dilutions of potassium permanganate and water. So I'm not going to tell you how much I'm going to use. Maybe you can cleverly see, but you're going to have to look at my numbers at the end and tell me how much I give. I'll tell you what the final dilution is if it changes, but you'll have to tell me what numbers I used. So hypothetically, it's like you're doing the lab. You're seeing what's going on. Woo! Sorry for the vocal fry there. But this is 0.001 molar potassium permanganate. So this is to test tube 1. Here's the only hint I'll give you. Of the 10 ml solution, I'm using exactly 10 mils of potassium permanganate and no water. That's the only one I'll tell you because it's going to be pretty obvious in a minute. Tube number 2. I'm not going to add all of it in. I'm going to add water to bring it up to 10. Ten mils. 3. Add water to get it up to 10. That's at 10. 4. tube 4. Tube 5. I'm going to fill up tube 5 with water. And there, that's good. That's up at 10. Lastly, tube 6. Finally, to fill up tube 5 to best of my ability to 10 mils. So all of them are being diluted from whatever volume to 10 mils. I'll give you the concentrations momentarily. Okay, good, perfect. Well then, as we look at our solutions, we have one that is 10 millimolar, 6.1 millimolar, 4 millimolar, 2 millimolar, 1.1 millimolar, or also known as 100 micromolar, and 0.5 millimolar, also known as 50 micromolar. And I have the unknown. Where does it fit in here? I don't know. I'm going to be testing these by UV-vis, just like we did last lab, to first make a calibration curve and then determine the concentration of the unknown. Before I determine the lambda max, I need to determine the maximum. I need to calibrate my spectrometer. So I'm squirting water into the cuvette, filling it up, ensuring there is no bubbles. I'm going to insert this into the spec 20. There are some bubbles, so give me a minute. Bubbles will absorb light differently than just plain water. So, cuvette, sensor, calibrate. Now I've already let this warm up, so I can skip warm up step. Just finish calibration. Okay, now that's done. I'm going to now put in my first sample and determine the wavelength max. I'm going to go ahead and use my middle sample. That's maybe a little bit... Actually, I'll go ahead and use the highest concentration sample. So I get the strongest results. But I'll still probably want to do this again. So I rinse it with my sample a couple times. Make sure I don't fill it all the way up. I'm just trying to coat the sides. But this wavelength max is what I'm going to use through all of my samples. So I just hit play, let it record, let it record, let it record. And it'll pick the highest peak. Right there, it's picked 522.7 nanometers as the wavelength max. Now it has a bit of that shoulder in there. I'm going to go ahead and record both for my sake. But 522.7, the absorbance is 0.579. So you can see that. And with that in mind, I'm going to start again from the lowest. I've already rinsed it out with some water, but now I'm going to rinse it out with some of my sample twice. I'm going to fill it up. Record it again. If we get the same max wavelength, we'll be fine. Let's do that. This one's going to be not nearly as intense, but okay, here, yeah. 23. So, I'll go to 527.7 if I can. Or 522.7. We'll keep it at that one. 522.7 reads 0.027. Pretty ugly, but this is the most dilute. 0.027. Rinsing out with test tube number 5. So that was 6. Now I'm doing 5. The reason I'm working upwards, I'm working from 6 back to 1, or at least back to 2, so that as I'm increasing in concentration with each sample, so that I less likely chance of contamination. So I'm recording this one. Oh, cancel. I'm going to go to 522.7, and that's going to be where we're going to keep peak. Moving over to 5. .067 reads 0.067 for number 5. Test tube number 4. Oh, a little bit too much. Well, first rinse. My idea is that if I'm mixing a more concentrated one in there, if there's any remaining sample left, the dilution factor will be much less significant, as I'm going from dilute to concentrated. Air bubble in there. Pesky little bubble. I'll have to throw off my sample. Okay, air bubble's gone. Put that in there. Record. Back on top again. So our 520, move that over. 2.7 reads 0.132. Okay. Down to test tube number 3, rinsing. Dumping in waste, rinsing. Dumping in waste. Now filling up. Test tube number 3. Okay. Move it over. Gotta stay consistent. Gotta use the same wavelength to get the best numbers. Okay, so test tube number 3 at 522.7 we have 0.224. Finally, test tube number 2. Boom. And done. And done. And finally fill. Wiping down the sides to make sure I don't have any smudges. Put in, record. Only need a few seconds to record because it's not going to change. At 522.7 reads 0.356.
At this point, we now have all we need to make our calibration curve. So we are going to graph a scatter plot of concentration of our 6 test tubes versus absorbance. We're going to make a scatter plot in Excel or Google Sheets, and we're going to draw a trend line through them. You're going to give me the equation of the line and the r-squared value. That r-squared value tells us how well the trend line fits the data that we actually have. That trend line is our Beer's law plot. Our Beer's law plot saying absorbance equals molar absorptivity times path length times concentration. Well, concentration is our x, absorbance is our y, then molar absorptivity is our slope. And of course, we have a y-intercept which doesn't normally appear in the Beer's law plot. So, but we'll have that, and that will be something we'll need in part C.
The last spectra I need to take is of my unknown. We are going to use our other data to find out what is the concentration of this unknown sample. I'm rinsing it out. Rinsing it out. That up. Double check and make sure there's no air bubbles, no smudges, nothing that's going to change how the light absorbs. Store that. Record. 522, oh, I'm moving one over, 522.7, got a reading of 0.289 for the unknown, 0.289.
At this point, we have all we need to finish our calculations. So what you're going to use is you're going to use your absorbance for the unknown. That is going to be your y. And now you're going to use your calibration curve, your slope, and your y-intercept to calculate your x. Because if y fits somewhere along that curve, we should be able to figure out where it would cross that line and be able to draw it down to calculate our x. So you're going to plug in y to your equation and solve for x, and that will be the last calculation of the lab. Good luck. So this has been the Chemistry Cowboy. Once again, if you like what you see, please like, please subscribe. I'll be posting more videos to give you the education you need. And I've been asked to put this disclaimer to Bethel students. Remember that the log and the online learning guidelines remain in effect while interacting with any type of instructional materials / sessions. That over and out.